the Indian Institute of Science in Bangalore, who's going to tell us why I care about vector spaces.
All right. Well, thank you very much, Daniel, and it's been nice to be here at this campus. I'm a novice with these kind of things, and so if I'm blocking something that should obviously be visible or have something shifted wrong, please let me know rather than well, if it's very funny, I suppose you can let me continue like that. But if it's unless you're really enjoying the incorrect slide, please let me know. So I'll try and do this. So today I'll talk about vector spaces, and of course one could probably give 100 lectures with the same title. And the point of view I'm going to have on it is the following question. So you all start, when you study linear algebra, with Rn. You've got n tuples of real numbers. And you know that you can add them and multiply them by scalars. A scalar is a real number. You can just multiply every entry in the column by some real number. Or you can add two vectors entry by entry. Okay? And so that is, you can say that Rn consists of objects which have the property that you can add them and you can multiply them by scalars. Okay? And then this tells you that it makes sense to define linear functions to be functions between, say, Rm and Rn, which respect these two operations. They're maps that preserve addition and preserve scalar multiplication. Okay? And so we can generalize and abstract this notion to a vector space, which is sort of the most general mathematical object where you can make sense of these two operations and they have the same properties that they do for Rn. So it's a set with two operations. One of them is the addition. So you take two different vectors in the space and you add them together and you get another vector in the space. So you've got a binary operation. Two vectors gives you another vector. And then you've got another operation called times, where you take a real number and a vector and you multiply the real number, the scalar, by the vector and you get another vector. Okay? And if you're defining this mathematically, when you have a set with these two operations, if you want it to behave like Rn, then you have to make sure that these two operations sort of have the same properties that the multiplication by scalars and the addition have on Rn. So you get this long list of things, in maybe your second week of linear algebra course. You have, this is the definition of a vector space. So it's a set V such that if you have, and I've just written it up for completeness, but these are the set of familiar rules. These are the things that you need these things to satisfy. For instance, that you should have distributivity over addition and multiplication. You have two different types because you have both addition of real numbers and addition of vectors. You have inverses. You have a zero vector. You have associativity of addition and commutivity of addition, etc. So this sort of captures the algebraic structure of adding things on Rn. Now, for particular n, for R3, you have other structures which aren't reflected here. So this is not exactly the same as Rn, but it reflects these two operations. Okay? So you hear this. So you say that there's something more general than Rn on which you can do these operations, and so therefore you can define linear functions. Because once you have, once it makes sense to take scalar multiplication and take vector addition, you can use the same definition verbatim of linear functions, right? Where you just say V and W are elements of some vector space. This is the condition for a function to be linear. Nothing needs to be changed. So you can say a vector space is the most general setup where you can define linear combinations and make sense of what a linear function is. But then the thing is, once you have a vector space defined, the first theorem that they tell you is the following. So first, recall that a basis for a vector space is a set of vectors that's linearly independent and spans the set. And then you have a theorem that says that if you have any two bases for a vector space, they have the same number of elements. If I have a vector space V, which has a 3-element basis, any other basis for the same vector space will have 3 elements. And so you have a well-defined notion of dimension, which is the number of those elements, the number of independent parameters you need to specify an element of the vector space. And a corollary of the fact that any two bases have the same number of dimensions, estimate the same number of elements, is that any n-dimensional vector space is actually isomorphic to Rn. So why is that true? Why does that follow? Well, if you have an n-dimensional vector space, that means you have a basis within elements. And you can make an isomorphism with an Rn, that is a linear map that's a bijection, that it's onto and one-to-one, by simply sending the ith basis entry to the ith standard basis vector of Rn, the EIs. And so if you send vi to ei, then you know what to do with an arbitrary vector because you've said that your isomorphism is supposed to be linear. Right? So you know for a linear map, if you say what the linear map does on a basis, you've determined the linear map everywhere. Okay? So this gives you an isomorphism to Rn. And so in particular, since any two n-dimensional vector spaces are isomorphic to Rn, you can compose the isomorphisms, and so they're isomorphic to each other. So in some sense, you could say there's only one n-dimensional vector space for any given n, and it's Rn. So the first question I think any reasonable person would have is, so why do we bother? Why not just talk about Rn? Why do we even talk about vector spaces of dimension n? Because if they're all Rn, what's the difference, right? Why do we have to have this abstract definition with all these funny conditions? Sorry. So that's an example of something where if it's funny, you can leave it there. But if not, please let me know that I put the wrong thing on the board. So why should you have the definition of a vector space? Why not just talk about Rn? Okay. So that's the point today. And there are several different answers one can give, sort of with different points of view. So I'll indicate a couple of them, but then I'll focus in on the one that's going to be my topic today. So the first objection you can make, the first reason that you don't just have Rn, is that sometimes you have infinite dimensional vector spaces. So Rn is a vector space of n dimensions, and any n-dimensional vector space is isomorphic to Rn. But the definition of vector space didn't exclude infinite dimensional ones. So for instance, you can look at the vector space of all functions from R to R. You can add two functions, and you multiply a function by a number, and you get another function from R to R. And if you add some conditions on the functions, then for appropriate conditions, you can get more vector spaces, such as the vector space C infinity of R, which is a space of smooth functions from R to R. Right? If you add two smooth functions, it's smooth again. If a function has a first and a second and a third derivative, and another function has the same, you add them, it's still differentiable. And you know the derivative of the sum is the sum of the derivatives, etc. Same if you have a smooth function, you multiply by 7, then you have another smooth function, 7f. Okay? And so that's an example of a vector space you actually really do want to study, which is not equal to Rn because it's infinite dimensional. So actually, I didn't write a slide for it, but why is it infinite dimensional? So one way you can see it is that you can exhibit a set of independent functions, an infinite set of independent functions. Namely, let's see if this... okay, I entangled it about 2 minutes ago, and now it's already done. So for instance, here's a set of independent functions. Inside C infinity of R. So the monomial x to the n for any n is a smooth function. And the span of these things here is a set of polynomial functions. Okay? And you know that two polynomials are equal as functions if and only if their coefficients are the same. So that means that these things here are linearly independent. If you have two combinations of x to the i's, say from I equals 1 to n, and that's equal to some other linear combination, if these are equal, then it has to be the case that AI equals BI for every I. Right? Because if you take a look at the difference between them, you have another polynomial. And this can only be the zero polynomial, the zero function, if and only if all the coefficients are 0. Right? You know that if a polynomial has infinitely many zeros, it has to be identically 0. So this tells you that this is an infinite dimensional set, because an infinite dimensional space because it has infinitely many independent vectors. It can't be isomorphic to Rn for any n. You could look at the space of polynomials of degree less than or equal to some fixed number, polynomials of degree less than or equal to 7. That's a vector space, and it's finite dimensional. But if you include all polynomials, that's infinite dimensional. So the smooth functions are obviously something we care about. That's what you study in calculus. And that's an infinite dimensional vector space, which is interesting. Now, maybe it's in a vector space, but maybe its vector space structure is not interesting, right? And you managed to study calculus without ever hearing about vector spaces, right? In your first year calculus class, probably nobody ever said the word vector space because you didn't need to. So you might ask, okay, yeah, it's got a vector space structure, but maybe it doesn't matter. It turns out, actually, though, that the vector space structure is very important. For instance, you've got an interesting linear map on smooth functions to themselves given as follows. You take a smooth function, and you send it to its second derivative plus itself. Okay? That's a linear map because if I take two functions, f plus g, that's equal to f plus g prime prime plus f plus g. But because derivatives distribute over addition, I can rewrite it like this. What did I want to do? Yeah. Oh, there we go. So I can write it like this. And similarly, if I have a real number alpha, sorry? Okay, thanks. If I have a real number alpha, then that's equal to, since alpha pulls through a derivative, that's equal to alpha times df. So that's a linear map. Okay? And it sends a smooth function to a smooth function. Okay? And the new function has infinitely many derivatives because the original one did. And the kernel of this map is interesting because it's the set of solutions to the differential equation f double prime plus f equals 0. Okay? Which is an interesting differential equation. And I've already written on the board, so I can't. This is something where my inexperience with the projector shows. I'd like to ask you what's the solution space, but I've already put it on the board. So sine and cosine are solutions to this differential equation because sine double prime equals minus sine, cosine double prime equals minus cosine. And it turns out, you can prove, and you probably do in your first year calculus class, that those are the only functions that satisfy that. Okay? And so any function that satisfies this is a linear combination of sine and cosine, which means that the solution space, which is, since it's the kernel of a linear map, you know it's a vector space, the null space of a linear map. And since it's got two generators, it's isomorphic to R2. Okay? So now, of course, you could say that, okay, that was interesting, but now we're back to R2 again. And so it's a two-dimensional vector space. Why do we care which two-dimensional vector space it is? It's R2. Well, the thing is, it's not R2 in a natural way. You have to make a choice to make it equal to R2. For instance, you can choose that 1, 0 goes to sine and 0, 1 goes to cosine, or you could do the reverse, or you could do something more complicated. I'll write down an example in just a second. But I mean to say that even though this is generated by two things, it's not obvious, at least, whether there should be some reason to make sine, that is, R2 is the plane. And if we say that the span of sine and cosine is isomorphic to R2, we're assigning sine some point in the plane and cosine some other linearly independent vector in the plane. And which one should you assign? So it's not obvious that there is some natural choice. There's some obvious choice. And if you make it maybe be arbitrary. In fact, I think there is no sensible way to. There is no way that's better than any other. Now, the thing is, maybe you could make an arbitrary choice and just work with it. So I'll give you an indication of why that actually won't work out so well. Right. And so, but actually, so I'll come back to that in just a second. But you could rephrase my original objection. So remember, I said that if all n-dimensional vector spaces are isomorphic to Rn, okay, infinite dimensional vector spaces aren't isomorphic to Rn. But say we're just looking at finite dimensional vector spaces. Okay. So say when we're working with infinite dimensional vector spaces, we have to work with which is called functional analysis, which is when you're looking at linear maps which are given by differential operators, and your vector spaces are infinite dimensional spaces of functions. That's called functional analysis. It's linear algebra souped up with some extra information. Like you might take into account smoothness and things like that. Okay? But so say you're not doing functional analysis. You're only working in finite dimensions. Then why not just do Rn for that? Okay, so let's modify the question. So if we're working in finite dimensional vector spaces, why do we care about anyone that's not Rn? And so the thing I was indicating there is that there might not be a natural way to identify something as Rn. Okay? Like here's another example. So, as I said, we have to choose a basis if we want to make it isomorphic to Rn. So here's another vector space which is given to you as a subspace of Rn. And it's two-dimensional, but there's not a natural way to identify it with Rn. So namely, I have this vector space in mind. You take all vectors x, y, z in R3, whose sum of coordinates is equal to 0. Okay? So it's a vector space. You can simply, if you like, you can write down and calculate that if you have two such x, y, z's and you add them together, their sum has that property, just algebraically. Or even you can be clever and observe that the way that I've defined it as the x plus y plus z equals 0, that's the kernel of the linear map x plus y plus z. And you know that the kernel of a linear map is, again, a vector space. So this is a subspace of R2, and it's two dimensions. One way you know that is that it's the kernel of a linear function from R3 to R. If you have a non-zero function from R3 to R, its kernel, if you have a function from R3 to R, its kernel is either everything or it's a two-dimensional space. That is to say, you either hit all of R or you have the zero map. So if you have a non-zero map, it's got a two-dimensional kernel. So this vector space here has to be isomorphic to R2. But the question is, which vector in this space here is E1 and which one is E2? You have to make a choice, and it's not obvious which one to choose because there isn't a natural choice. Oh, and maybe I should just draw a picture of that. So this vector space, if you draw it inside the plane, inside space R3, it's a plane that's not parallel to any of the coordinate axes. So here's the point 1, 0, 0. Sorry, that's not the right one. I won't. Sorry. 1, 0, minus 1, say. And then, I'm not drawing this right. And then, say z is 1 and x or y. So it's a plane that goes through the origin. My picture is awful, but it's sort of it's coming through the origin at an angle. I'm not going to achieve this with my picture. But my point is that whereas if I had a vector space that was, say, two of the coordinate axes, I have another vector space inside R3 that actually does have a given basis. That is to say, if I look at a span of 1, 0, 0 and 0, 1, 0, well, I could view this as the two-dimensional xy plane inside R3. And you would be reasonable if you wanted to identify this with E1 inside R2 and this with E2 inside R2. So if you have a coordinate plane inside a bigger space, then it would be actually natural to decide which coordinates to give it. But if you have something that's not parallel to the coordinate axes, you have to make some choice because there is no vector that points in the E1 direction. There is no vector that points in the E2 direction because the thing is not at 90 degrees to the coordinate planes. So you have to make a choice. Like here's two examples. Here's two different bases for that vector space. You could take 1, 0, minus 1. Or you could take 0, 1, minus 1. Or you could take 1, minus 1, 0, 1, 1, minus 2. Okay? And when you're writing down the isomorphism, what you're saying is that you choose a linear map, in this one case L1, that sends this basis vector to E1, this basis vector to E2. Similarly here, we've got L2 that sends this to E1, this to E2. Now, why doesn't that settle the question once and for all? So actually, I did it with the sine example. The thing is, now if you want to look at linear maps, so you'd think that by re-identifying your vector space as R2, you've solved the problem. You've reduced it to linear algebra in R2. Thank you. The thing is, but linear algebra is not just vector spaces, it's vector spaces and linear maps. So if you have a linear map on your vector space and you identify the space with R2, if you want to see what map on R2 it corresponds to, that actually depends heavily on your choice of isomorphism. That is, so remember that so if I have a linear map, choosing a basis on my space gives you a matrix. And so what matrix you get depends on which basis you choose for a fixed linear map. So for instance, if I choose the vector space isomorphic to R2 that I had a minute ago, the solutions to the differential equation f double prime plus f equals 0, it's the kernel of that map that is generated by sine and cosine. Okay, and I've got a map from that space to itself given by the derivative. The sine and cosine happen to have the magical property that the derivative of one is equal to the other derivative of the other is equal to minus the first. Right? So if I differentiate anything in here, I stay inside the set. So cosine derivative is minus sine derivative is cosine. Okay? And these are both, and differentiation in general is a linear map of vector spaces. And I can ask, what is the matrix for this map of R2 to itself, this linear map? Well, it depends on the matrix, on the basis you choose for the vector space. So for instance, if I chose cosine to correspond to E1 and sine to correspond to E2, I would get this matrix because, let's see, 1, 0 would go to 0 minus 1. Okay, cosine would go to minus sine, and sine which would go to cosine. But if I say switch them, right, so the most obvious things to do if I hand you the vector space generated by cosine and sine would be to make one of them E1, the other one E2. But even if you just take that as given, you have to decide which one is E1 and which one is E2. And so if I make the other choice, I let E1 go to sine and E2 go to cosine, I get this matrix instead. Well, it's almost the same as this one here. It's just off by an SIGN sign. Okay, but what if I choose this other basis? And the thing is, I've handed you the basis sine and cosine. In this particular case, we've got famous functions called sine and cosine. It's convention, but we say that, but those are the most natural functions inside the kernel here. But say you were doing some sort of mathematics from some funny point of view, and you came up with, you decided the basis for this vector space should be 2 sine x minus cosine and sine x plus 2 cosine. Okay? So if that was your basis, and I wrote down the derivative map, this would be the matrix for it. I happen to calculate it. I won't do it now. You all know how to do this from your linear algebra course, but it's something that looks nothing like these two matrices. Okay? Now, they're not totally unrelated. You know very well that if you change between bases, the linear maps, the matrices for the linear maps are conjugated by the basis change things. That is, if I have some change of basis matrix T, and then the matrix for L goes to T, L, T inverse, something like this. I won't write down the details, but you've all seen it before. And so it's not completely unrelated. And for instance, in any two bases, the matrices for the same linear map, one will be invertible if and only if the other one is. So there's a lot of properties that are preserved, and somehow all the information is there. It's just sort of translated in some complicated way. But the thing is, this map was very natural. This was a very intrinsic map that was natural from the point of view of the way that we saw the vector space. Whereas if we translate it to R2, in R2, there isn't a natural differentiation operation that sends R2 to itself, right? It's only when we interpret R2 as the kernel of this operator, as a space generated by sine and cosine, that this map is natural. Once I translate it to matrices, if I hand you this matrix and I don't tell you where it came from, you don't look at this and say, this is differentiation. So this is a reason, anyhow, why it might be nice to look at vector spaces without viewing them in terms of R2, because sometimes it might be more natural. I mean, it's sort of, if you construct the vector space in a certain way, some operations on it might be nicely stated in terms of the way you construct it. But also because if you translate it to R2, you've added some arbitrary step, and you can no longer say, this is the linear map. The linear map isn't this. It's only this in some particular basis. So you have to remember the basis. And so any calculation you do in a basis, you have to, if you translate this to R2, and you do any calculation, you have to remember what the basis is. You can't forget it. Because if you ever want to translate back to sine and cosine, you need to know how to translate back. So this isn't intrinsic. Okay. Now, this is how it was explained to me the first time I asked this question, back when I was probably your all's age. And it's a reasonable answer. I mean, I think there are some aesthetic reasons to think that choosing a basis that is, remember, making an isomorphism of vector space to a specific Rn is the same as a choice of basis. Who said it? Someone says that choosing a basis for a vector space is an act of violence. You shouldn't do it because aesthetically, so we've just seen in this example, it sort of obscures what's going on with this operation on the space. In other situations, you might be able to prove something in a basis, but maybe your proof is just a calculation. You don't see what's going on. Whereas often if you do a proof that doesn't use a basis, you sort of see what's going on sort of intrinsically. You often have a lot of theoretical insight that you don't have otherwise. But the thing is, anything you can do with a basis without a basis like that, you could also do with a basis, and usually more easily. So you can say, this is nice, but if I want to work with bases, maybe I have to keep track of which basis I'm using. But you can always do it. Okay? So now I'm going to talk about when you can't do it. When you can't do that is if you want to consider many vector spaces simultaneously. Zoom out? Yeah, thanks. So I may have just written on my only blank. No, I haven't. So if I'm considering a family of vector spaces, all of dimension n, so these are vector spaces of the same dimension, I might not be able to simultaneously identify them with Rn in a way that makes sense. So let me explain what I mean by that. So if I have the sphere, which has the mathematical name S2, this is the usual sphere in three-dimensional space, the points in R3 such that x squared plus y squared plus z squared equals 1. Okay? And this object called TS2 is called the tangent bundle to the sphere. At any point on the sphere, you have a set called Tp of S2. So if P is a point on the sphere, geometrically you know what it means for a plane to be tangent to a surface. It's the plane that sort of kisses it, the plane that is sort of as close an approximation as you can have. So for curves, like the graph of a function, you know very well what a tangent space is. It's the line that has the same slope as the function does at that point. That is, the derivative of the function will equal to the slope of its tangent line. That's, in fact, sort of how you define derivatives. If you have a surface where you have two parameters of freedom, where you can move around in sort of independent directions, you can ask what plane is tangent there. And so, and for the sphere, you can write it explicitly. A vector at a point P is tangent to the sphere if you view P as a vector in R3. Right? It's a point in R3. We can view it as a vector if we want. We can view it either as a vector from the origin or as a point on the sphere. So if you view it as a vector, and we take a look at a tangent vector to the sphere at that point, they should be perpendicular. Right? In the case of a circle, that's very clear. I mean, and it's not really any different. You know very well that I feel like I'm, when some people attach a rope or something to little kids, or to a dog or something like that, I feel like this right now. This is so that I don't run off and go to a hawker center when I'm supposed to be giving a lecture or something. Right. So geometrically, you can see that here's the tangent space to the circle. And you see that the tangent line to this here is perpendicular to the line from the origin to the point on the circle you're considering. So there are fancier mathematical definitions that work in more general situations, but for our purposes today, all we need to do is think of this TPS2 as the tangent space to the sphere at that point. Okay? And now, the tangent space to the sphere at the point, it's a plane, so I could identify it with R2. Now, why should that be a vector space? I've got this plane attached to a point on a sphere, so why should I be able to add things in it? Well, you can see it geometrically, because if you have two vectors that start from here, you can just view them as, if you like, vectors in R3, and because they're both tangent to the sphere, their sum will be tangent to the sphere. And so here's a vector, here's another vector, here's the sum of the vectors. Right? If you have two vectors, you add them, if they're both perpendicular to the same thing, their sum will be perpendicular to the same thing. Actually, that you know because, if you think of perpendicular in terms of dot products, and you have the sum of two things, if you add two things together and you take the dot product with something that's perpendicular to each of them, it will be perpendicular to their sum because the dot products add. So this thing here really is a vector space because I can add two vectors in it and I can multiply any one of them by a scalar. I just have a longer vector. Here's W and here's alpha times W. Let me make a picture. I have W and alpha times W, which is starting at the same point here, but just going further in that direction. So I've got a two-dimensional vector space at this point in the sphere. So just for some fixed P for now. We'll worry about the entirety of the sphere in a moment, but let's just focus on P in this tangent space there. So it's a two-dimensional vector space. From what I said before, you can identify it with R2. And you can say make V correspond to E1, W correspond to E2, and therefore you can view addition and scalar multiplication in terms of R2 itself. Okay, so this just brings you back to where I said before. Why do we need to consider this vector space as a subspace of R3 that's perpendicular to some fixed vector in the sphere? You can just think of it as R2. The thing is, what if you want to do this for every point on the sphere at the same time? So this object called TS2 is the union of all the tangent spaces to all the points here. Okay? So what if we want to simultaneously identify all these things to R2? Okay, what would that mean? So for any given point P, as I said, we can identify the tangent space to the sphere at P with R2. That means we've got some linear map, phi sub P, that sends this tangent space to R2. Say it sends some vector, which means that some vector will go to E1, some vector will go to E2. Right? Or you could say that V is equal to phi P inverse of E1, if you like. Okay. And now say you could do this for all points in the sphere. Then you could ask for then that would mean for every point on the sphere, you have one vector that you identify with E1 and another vector you identify with E2. So this is what's called a frame for the tangent bundle. That means that you've got a pair of vectors at every single point on the sphere. Here I've drawn a picture. So I've just drawn a couple points. I can't draw all infinitely many at once, but you see here that for each of these points here, I've got a pair of vectors. The one I've labeled as W is the one that's supposed to correspond to E1. The one I've labeled as, E2, and the one I've labeled as V corresponds to E1. Question? Yes. So I'm not necessarily, at this point, saying that my linear map has to preserve dot products. So you could do that, actually. It would work out fine. But here, so just to say that I identify E1 with E2, V with E1 and W with E2 via a linear isomorphism. The only thing without adding some extra condition, like you say, which in some situations we will do, and actually I may mention in a few minutes, the only condition it puts on V1 and V2 is that they be linearly independent. They don't have to be orthogonal. They don't have to be unit length. Right. So if we have this phi p for every p, then that means that at every point here we've got a pair of linearly independent vectors that are each tangent to the given point on the sphere that they're tangent to. For each point here, I've got a tangent vector v and a tangent point vector w. They're linearly independent from each other. So you could view this as sort of a frame, not necessarily an orthogonal frame or an orthonormal frame, but just a frame, a pair of independent vectors that's moving around as I move over the surface of the sphere. So here you've got it varying a little bit as I go here and there. Maybe it twists around. It doesn't have to. You could try and make one that sort of twists minimally, or you could have one that just sort of twists every which way. It can rotate around in circles as you go along. I could be doing this as I move along the sphere. Okay. And so if I could simultaneously identify all the tangent spaces to R2, then I would have such a thing. Oh, notice, by the way, that implicit in what I said is that I want these two vectors to vary continuously. So it can be formalized, but it's exactly what you think. If you were to draw a picture of how, make a movie of how any one of the V or W's moves, you should have it, if you say, actually, the tip of a vector is actually a point in R3, right? You start at a point, so VP is a vector starting at P and ending at some other point, and the other point is inside R3. And you can ask, as I move around in the sphere, that the tip of the vector should move continuously in R3, okay? So we want to impose this thing here. If you didn't impose it, then actually we would essentially be having one vector space for every point on the sphere, and if there's no relationships between them, then sure, you can take every vector space there, identify it with R2, and then you've solved the problem. You've identified every point with every tangent space with R2, but the thing is, this forgets that they were attached to the sphere. Like if at some point here I've got a vector that points like this, and then it jumps to some vector that points a different direction, somehow you're losing the geometry there. So that's somehow actually not, it wouldn't be an interesting thing to look at. So the interesting thing is if you want these vector fields to vary continuously. And the question is, can you do this? Can you find a frame that varies continuously on the sphere? So let's try and do it. So let's make a naive attempt. So one thing we could imagine doing is identify some particular point tangent space with R2, which means that at that tangent space we have two vectors. And let's just sort of draw what would happen if you move the vectors around. So at some other point, so I start here, I draw my V and my W. And so then at some other point here, I'll just draw a way to sort of translate this vector down. Because remember, the identification of the vector space with R2 is the same thing as choosing a pair of independent vectors. That is, I'm choosing a basis for each of these spaces. So if I just sort of draw the vectors at every point, then I've done it. I could translate that into algebra afterward if I like, but somehow this is a geometrical question. Okay? And so say that, so this thing here, I've got a certain path here. And so I've got a, is this a longitude? This is a meridian. Okay. This is a meridian. This is a line from going from the North Pole down to the South Pole along a great circle. And if I were to, so I can't do it in here, but so I've got my sphere here, and I've got a pair of framing vectors up here. So I could simply translate this around like this, down to the South Pole. So every point along this great circle here, I've got a pair of vectors just by doing this. Okay? I'll say more in a little bit about sort of how much flexibility I have to make this choice, but or about some systematic ways to make this choice. But certainly I can try doing this, and this gives me a frame for every point along this meridian. Now, but then I have got the rest of the sphere to take care of. I've taken care of one curve on the sphere, and I've got the whole rest of the sphere to fill in with this vector field. And say I try and do the same thing in some other direction along some other meridian. So here, say this was the line of 0 latitude or longitude? Latitude, right? No, longitude. Longitude. Okay. So this was along the line of 0 longitude. So say I do it along the line of 90 degrees longitude. So along this curve here. So before I did this, and notice that this vector here that in three-dimensional space was pointing this way, at the end of my path points like this. Whereas this one here is still pointing in that direction. I'll say that. I'll draw a picture of that in a second. But say now I go this way instead. Then I'm following this thing here. Right? I told you this is telling you what each of these vectors is at every point along this meridian. So I bring it down to here. So notice that this vector here always still points this way. And this vector here, my index finger, that's pointing this way now, at the south pole will point that way. And let's compare these two things. Because remember, in the end, what I'm trying to do is get at every point a frame. And so in particular, that has to be consistent. That is, at the south pole, I have to have a single frame there. And so this naive attempt of just sort of taking one frame and pushing it around is going to give me a problem at the south pole because, so again, if my thumb is V and my index finger is W, at the bottom, V and W have to have a well-defined definition. So here, my thumb, V, will be pointing into me, whereas if I do it like this, my thumb, V, will be pointing that way. And so I may have to make a choice. So this didn't work because I've made, at least, maybe I can fix it, but at least this first naive attempt didn't work because now I've got two conflicting definitions for where my thumb should be pointing. It should be pointing here, or it should be pointing here. So here's a picture of what happens there. So I've taken the bottom, sort of a spherical cap at the bottom, and I zoom in here. So this is supposed to be the bottom of the sphere, and I'm looking at it from the top. So when I took this vector here that points inward, and I pushed it out like that, it's going here. Whereas if I, that's right, and W is pointing that way. So this comes from the first path. So I started from V pointing this way, now it points this way here. And, oh, thank you. Zoom out, fine. Thanks. Sorry. Right. So here my V is pointing in sort of out of the screen, and here it's pointing into the screen, and so it's pointing in the opposite direction from the V that comes from the second path. So the V from the second path is pointing the same direction I started with. Again, it's this. I guess my hand pictures are probably clearer in this picture here. So again, we've got this versus that. So they disagree. Okay. So, but I haven't proven that you can't do it. I've just shown you that one sort of simple-minded attempt to do this doesn't work. Maybe I can this path here like this. Maybe I could twist it along the way. I certainly could, in fact. I could. So here I have this, and I say I want this, at the south pole this to be my hand position. So here I could do this. I just simply twist along the way, right? That will fix that problem at least. Okay. But and then you can ask, can I extend my fix over the whole sphere? Okay. So I won't be able to prove it in full, but it turns out you can't. I'll explain a little bit about why you can't do it, but then I'll give you an analogous, slightly simpler situation in which we can actually make a proof. There's something called the Hairy-Ball theorem. So if you get interested in this, you can look it up on Wikipedia or on the web and get lots of nice pictures and proofs. But it says not only is there no frame of tangent vectors at every point on the sphere, you can't even find a single non-zero tangent vector at every point on the sphere. So they call it the Hairy-Ball theorem because you imagine you've got a ball which on its surface has a hair sticking out at every point, and you like to comb it. And by combing, they mean like, instead of having your hair stick up like this, comb it so that it's pointing tangent to your top of your head. And the thing is, I can comb my hair even though I haven't, because I only have hair around here. And in fact, it's actually going, where my hair starts is going further back, even probably in the course of this lecture. But it never covered my forehead and such. And so so a human can comb their hair because they don't have hair everywhere on their head. And in fact, you've got a neck anyhow, so the bottom is not an issue. But say we abstracted this problem, right? This is what mathematicians do. They take a head and they remove the neck. They assume that you've got hair on your forehead and all over your ears and such, and you've got these grotesque things. And so you've got a ball here, which has got a hair at every point. You want to comb it in such a way that at every point the hair sticking out is tangent. And it turns out you can't do that. At every point you'll have to have, well, I mean, if you try and do that, well, it simply won't work. If you want it to be unit length, there's no way to do it. And if you were to try and view it, there's another way to think about it, that so say we view the sphere as the union of the top and bottom halves, the northern hemisphere and the southern hemisphere. And so we can reduce the problem of drawing the vectors on the whole sphere to the two problems of drawing a vector field on the top and drawing a vector field on the bottom, such that they match up in the middle. Right? If I have a vector field in the whole sphere, I can simply cut it in half. And if I have solved the problem on the two halves in such a way that they match up when they join, then that will give me a solution to the problem. And so you can see this. You can draw pictures for yourself. Like, so what this picture here is, it's, say, the lower hemisphere, where I've sort of flattened it into a disk. And flattening into a disk doesn't really change the essence of the problem. Right? I mean, you can imagine that you have this disk on the page, and if you on my desk and here, and if you had a combing of it, if I were to, this was made out of clay, and I sort of flattened it down, then if a vector was tangent here, it gets pushed down to a tangent vector there. So somehow this is what you call a topological equivalence. That somehow you haven't changed the problem intrinsically by just changing the sort of shape there. I mean, it's still a disk. It's just a curved disk versus a flat disk. And for this purpose, they're the same. And so here I've got a flat disk by flattening the hemisphere. And so here's an example of a vector field on the edge of it. And the question is, can you extend it to the interior as a non-vanishing vector field? Because remember, a frame has to be two independent vector fields. In particular, they're both non-zero. And the Hairy-Ball theorem says that you can't have a single non-zero vector field everywhere. You can't even have one linearly independent vector field in that space. And so if you have a given vector field on the edge, that is to say it's tangent to the plane. So I'm drawing so this is really honestly a two-dimensional picture. It's tangent to the plane at every point. So actually, let me say that I'm really starting out with a vector field on the circle that's the boundary of the disk, and I'm asking, can I fill it to the interior? Well, here's one way to do it. You sort of just shrink it down, and you find, in fact, that if you sort of try and extend it radially, so that along, say, the vertical line, that all these vectors are pointing in the same direction as the one at the edge. And so along this line, horizontal line, all the vectors are pointing in the same direction as the one at the edge. The thing is, when you get near the middle, they're all pointing in different directions, right? Because if you look at the way that these are pointing as you go around the sphere, the vector fields themselves are rotating. Here it's pointing this way, here it's pointing that way, here it's pointing this way, here it's pointing that way. And so if you try and extend this to the middle, you'll find that in the middle you have a point at which the vector field would have to point in all possible directions. And that simply doesn't work. The only way to extend this continuously is to, at the point where it have to be pointing in all possible directions, you just simply shrink down the vector, and so it's a zero vector. You can say the zero vector is the only vector that points in all directions. But more importantly, you can say it's the only way to extend this thing here to a continuous vector field. So you have to have a zero. It won't be a non-zero arrow. And then I didn't fill this one here. So if you ever try and do it radially, you'll have the same problem here. And so you can write down vector fields on the disk that don't have a zero. Like, for instance, the one that's always pointing in a constant direction. That's actually OK. But the thing is, if you view this on the other half, then you'll find that from the point of view of the other half, this vector field is twisting on the edge, and you won't be able to extend it. So this is something where, to prove it carefully, actually does require a bit of machinery. What I've just said now, you can actually convince yourself of. I mean, just it's one of these things that's better to spend 5 minutes with if you're interested in it, to do it. Just try and draw any vector field you like on the boundary of a circle and try and extend it both ways. And you'll find that no matter how much you think about it, you can't do it. And then if you ever take a differential topology or algebraic topology course like the one Daniel's teaching, you learn how to do this rigorously. So it won't work. But I'm going to give you a sort of simpler example where we can actually show why it doesn't work. It's an example which is sort of less natural to come up with, but it's easier to work with mathematically. So it's the Mobius strip. So it's not the usual Mobius strip. The usual Mobius strip, you take a strip of paper and you twist it and you glue it back together. So it's a finite strip here. But instead, I've got an infinite version. I've got, for every point I've got a collection of R the real numbers, the one-dimensional vector space, that twists around as I come back. So it's like take a regular Mobius strip and replace each line segment with an infinite line. And so it looks like here that when I twist it around, so if I've got two sides of the Mobius strip, my Mobius strip looks like this. This one here might intersect this one here. So let's pretend those intersections don't exist. There's a mathematical way to say it, but I'm not going to consider these the same point. I can consider, I'm going to remember any point on this infinite Mobius strip remembers the sort of point it starts at. So you can consider this point here and this point here to be different points. It seems like a funny thing to do, but it turns out to be natural. I won't say more about it now, but but it doesn't really come into discussion. So whereas before we had a two-dimensional family of two-dimensional vector spaces. What do I mean by that? At every point in the sphere, which is two-dimensional, I have the tangent plane, which is two-dimensional. Here, I can view a Mobius strip as a family of, well, if it's the usual Mobius strip, as a family of line segments that twist around. So I can take the line through the middle of the Mobius strip, and then at each point here, I can attach a little line segment, and that line segment twists. In this case here, what I have is a circle, and to each point in the circle, I attach a one-dimensional vector space, a copy of the real numbers. And this copy here twists as I go around. That seems like a funny thing to do. What does it mean for a copy of the real numbers, which is not sitting inside space, to twist? Like, what does it mean abstractly for that to twist? Well, actually, one way you can view it is like this picture here. So I can view it as the real numbers cross some closed interval, 0 to 1. So, here it is. The interval 0 to 1 cross R, so it has an infinite strip. It's finite in this direction, infinite in the other direction. And just like a Mobius strip, I can take a rectangle and glue together the edges. I'm going to glue together the infinite edges of this thing here. And that's what we mean by an infinite Mobius strip. Now let's ask, can we simultaneously identify every one of these lines to the real numbers? Right? So every one of these lines is a copy of the real numbers. And so because a one-dimensional vector space is isomorphic to R, I can make the identification for every single one. The question is, can I do it simultaneously and continuously? Let's try and do it. So remember that if you have a one-dimensional vector space, linear algebra gets kind of trivial when you're doing one-dimensional things, but it still makes sense. In a one-dimensional vector space, what's a basis? It's a single linearly independent vector, and for a set of one vector to be linearly independent means that it has to be non-zero. So a choice of any non-zero vector in a one-dimensional vector space gives you a basis, which is an identification with R. So essentially what you're doing is picking out, in any vector space, and in a one-dimensional vector space in particular, you have a given 0. That's part of the structure of a vector space. And to identify a one-dimensional vector space with the real numbers, you know which one is 0. You have to say also which one is 1. Once you know what 0 is and what 1 is, you can label any other point by scalar multiplication. So let's try and find, in every one-dimensional vector space here, which point is 1. Well, we can just simply draw it. So here on this thing, so here we might as well be working with a Mobius strip because because I'm just drawing you an example of an attempt to find a non-zero vector in each vertical segment, right? So each vertical segment here you can view as either a finite interval or you can view as the whole line. But so what I want to do is find a non-zero element. That is, so 0 here is this circle here in the middle. So in any segment here, I've got a vertical segment, I've got a 0, and I'm trying to find a non-zero element of it. So say I start here. Well, if I've got a non-zero element here, then I've got to find a non-zero element in the nearby copy of R. And so that means I've got a point here, and they vary continuously. Right? Because remember I said that I want my basis, my frame, to vary continuously as I move around. I don't want them to be arbitrary. And so I can follow this thing around. I'm following it around the back. Hopefully my picture is clear. So I draw a vector at every point that's non-zero. And because it's non-zero, it means that it's got to be pointing, at least along this half at least, always pointing upward. Because remember, if you've got a positive real number, you can't, and you've got a continuous function, it can't cross to the negative numbers without passing through 0. This is called the intermediate value theorem, which I'll employ in just a second. Right? So if I have things that are always on one side of 0 and they're continuous, they have to stay on one side of 0. Right? So I follow it around, I follow. It's always above that thing. But the thing is, here I have this twist. And when I have this twist, so you can imagine my pen to be my non-zero number in every fiber. These vertical lines are called fibers. So in every vertical line, I've got the end of my pen is a thing. The thing is, when I bring it around, I twist, and now it's pointing downward, right? Because that's what's happening here. And now I'm pointing downward here. And when I get back to where I started, I now have a conflict because I've already defined in this fiber, I've got this one that points upward, and then everything here points downward, and when I get to here, I'd better have something downward by continuity. So I have a contradiction. If I have a continuous choice of non-zero vector at every point starting here, when I get back around, I'd have to have a negative thing or something pointing downward. That seems like, again, it's very weird the first time you see it, but it's actually easy to state in this case, the reason I chose this one, in terms of a function, because if I view this as 0, 1 cross R, with the edges sort of glued together by a twist, a choice of a point in each of the vertical segments is just like a value of a function. So that is, I'm just telling you the height at every point. And the thing is, this thing here, when I glue this together, I glue it with a twist, which means that I glue this point here to this point down here because I'm flipping over. And so if I've got a function here that starts out positive, when I glue it over here and I transfer to this side of the picture, it goes down to negative. And so what I'd be really looking for is a function from 0, 1 to R, that is, along every vertical segment here, I choose a real number. And such that the value here at, say, 0 is equal to the negative of the value at 1. Okay? So I'm looking for a function with this property. And the claim is that any such function has to have a 0. That is, there is no non-zero function with this property. And why is that? Well, either I start out at 0, in which case I have a 0. So either f of 0 equals minus f of 1, and they're both 0. Right? So if I start here, I can go above it and then come back down to here. But the thing is, I start out at 0, so I have a 0. If I start out at some positive number, if the function f of 0 is positive, then f of 1 is equal to the negative of it, so it's negative. So the function here is positive, here it's negative. By the intermediate value theorem, in between it has to hit 0 sometime. So this thing doesn't exist. So the intermediate value theorem here translates into the fact that this thing here is a non-trivial family of one-dimensional vector spaces. That is, I can't choose a simultaneous coordinate on each one of them. I can't tell you, sort of in absolute terms, in any consistent way, that this point here and this one is the number 3, the vector 3 in the real numbers. Because I can't do it in such a way that makes sense for every single point. So this means that, so the hope of reducing all linear algebra to linear algebra on a single copy of Rn is doomed, because if you ever want to work in families, it doesn't work. Now the question is, why the hell would you ever want to work in families? Like, this seems like a bizarre thing that I came up with to show you that your familiar thing doesn't work. But you probably never thought of this. Why was this a problem, right? I mean, this wasn't the problem until I showed up. I came from India, got off a plane, told you this thing that you already knew and thought was just fine was a problem. So here's why it's a problem. Because, well, it's a problem, but it also gives you some hope. So why would you want to study these things here? So say we're on the S2 example, like I told you before. Here's why you'd want to study the space of tangent spaces to S2. So it turns out that looking at the space of tangent spaces and the way that vectors move around when you push them around, like I was doing when I was trying to construct a basis, when I was trying to construct a frame, I was pushing vectors around. So you can use procedures that involve pushing vectors around to measure geometric things about your space. For instance, the curvature. So we all know intuitively that the plane is flat and the circle and the sphere is curved, right? We all knew this from childhood. But the question is, what do we mean by that mathematically? How do you prove that it's curved? Like, for instance, one precise way to make that statement is that if you have a flat piece of paper like this and you want to glue it to a sphere, that is, say, for instance, you're in the business of making globes, and you want to print out your map on flat paper and then glue it up to make a sphere. It turns out you can't do that. Your paper, you'll have to actually come up with some special curved paper that's been warped somehow. I don't actually know how the map makers do it. They're very clever people. But you can't just do it by sticking something in your printer and gluing it on, because it just simply won't glue on properly. Right? I mean, you can take it home and do it. I mean, you think that maybe I'm just being stupid and of course you glue it on, but it really won't work. You'll have to crease the paper. But even creasing and tearing won't be enough, because even locally it won't work. Right? So that's somehow a sort of concrete way you can say that this is flat and the other one is curved. You can't sort of stick this one onto the other one without making some distortion. If your paper was made out of rubber, so if you had a rubber sheet, of course you could wrap the globe in it because it stretches. But when you're stretching, you're changing curvature. The question is, can you, without changing distances, without stretching, paper some surface with sheets of paper? And if you can do it, it means the thing is flat, and if you can't, it means it's curved. Another example, besides a less familiar example, I don't have a picture, but is a saddle of a horse, or the crotch of a pair of pants, or something like this. And you can't with flat things, you can't glue a piece of paper onto there in such a way that it fits perfectly. You try and put this in the saddle, and the thing is, it curves down in the right directions over here, but then the saddle curves upward, and this piece of paper doesn't. And so it just simply won't work. And so what if we try and measure this failure to be able to glue flat things onto curved things? So what you can do is you can take a vector, fold it, and then push it around the path. Okay? And the interesting thing is, so remember with a Mobius strip, the reason that you couldn't make a sort of universal coordinate system on it was that if you push this vector around the curve, it flips down and doesn't come back to itself. It comes back to something else. But you can make a virtue out of this failure. So you can ask, if you push some vector around, like here's a path. So what I've drawn here is I've got this piecewise smooth path. I've got a path with corners in the sphere. These are supposed to be parts of meridians. And here's a piece of some latitude. And so if I push this around like this, my tangent vector to the curve here ends up here. Now I'll push it along here, and I'll push it back up along this curve. And you notice here that you start out with a tangent vector to this, and you end up with a tangent vector to this, and they're not the same. So I push, again, the picture is like this. I take my tangent vector at the North Pole, I push it down like this, I move it over like this, and then I bring it back up, and then it's not where it started. Okay? And you can measure that, because it's, so the way I did it, actually, it didn't change the length of it, or at least with my pen didn't change in length when I did this. It just changed in position. So it just was rotated by some angle. Right? If you have two vectors in the plane of the same length from the origin, they just differ by a rotation. Right? And so you can measure the angle attached to that. And that thing is called the holonomy. There's a fancy word from Greek probably that tells you, that gives a name to what happens when you take a vector, you push it around the path, and comes back to something else. So the difference between what you started with and what you ended up with, you can view as a map. It depends on the path, and it says that if you take this particular path, you start out with this vector, it gets sent to that vector. So in fact, if you fix a path, then this gives you a linear map from that tangent space to itself. And it's, in this case, actually, it'll be a rotation. And so the holonomy around some curve in the sphere is a rotation. So in particular, if I took two vectors, two different vectors, they'll be rotated by the same angle. So if I have a frame, I can view this as a rotation of the frame. Now, the interesting thing is that you can make some. So for every path, you've got this angle of rotation. So how do you really get something sort of concrete out of it? Well, essentially, you can say, actually, the angle of rotation is something concrete for this particular kind of path. But in general, what you can say is you can make some small sort of square in your space. Maybe it'll be a square with curved edges, but like say some quadrilateral. You take some vector, you move it around these four things, and you come back to something else. Now, it turns out that if that the amount of angle change will actually be proportional to the length of the sides of the squares. In fact, it'll be proportional to each of the lengths separately. That is, if I move along here, sort of infinitesimally, it changes a little bit. And then if I move it this way, it changes a little bit. And so if I'm going in this direction and in this direction by some amount, sort of the length of each of these things here, the amount of angle rotation is going to be proportional to each of them separately. And so if I make each of them some multiple of epsilon, it'll change infinitesimally by epsilon squared. That means that essentially, if I divide by epsilon squared, and then I take the limit as epsilon goes to 0, I should get some number in the limit. That's very sketchy, but I mean to indicate that by measuring very small squares and asking, so if I don't move at all, of course I'm not changing anything. But if I make some very small change, if I may have some very small path and follow it around, my rotation will be very small. So I don't want to just measure the rotation. I want to measure sort of the ratio of the rotation to the length of the path, or in this case, the length of the path squared, because that turns out to be the right multiple. And so by doing this, I get a concrete thing out of it, which is called the curvature. And so how much should I started a bit late.
Maybe 10 minutes.
Okay, but when did I start?
5 minutes. It's affected it.
Oh, okay. It says 2:37 there? No. Okay. So let me just spend 2 minutes just to sort of tell you where I was going with this. So this thing is called the curvature. So this is exactly how you make precise the usual definition of curvature that you have intuitively. Like, for instance, this thing will be 0 if and only if for a surface. So I gave you the examples here, but you could imagine for any other surface, you could do the same thing. Tangent spaces at every point, push around vectors. You have to say how you're pushing vectors around. For surfaces in three-dimensional space, there's a sort of natural way to do it. You push them around so that the lengths don't change and such that the angle with the tangent vector to your path stays constant. So there's a sensible way to do it. In general, you might need to actually tell you to say which isomorphisms you have between different tangent spaces. That is how you push vectors around. But you can do this, and then the curvature is something that measures how much it twists. And the curvature has the property that the curvature is 0. This limit I described right here will be 0 if and only if you can cover your surface with a sheet of paper without twisting or tearing. Now, it turns out that this curvature is a very fruitful thing to look at. I mean, it turns out that it has lots and lots of applications and things that sort of have geometry behind them. So one of them, the most famous one, is sort of the reason that the world knows about this kind of geometry at all. It's general relativity. So in Einstein's general relativity, and this is all I'm going to say about it, but then I'll say something more about some other example very quickly. In four-dimensional space-time, so you've probably all heard that in general relativity, you don't just look at space, but you consider space-time together as a geometrical object. And the distribution of matter warps space, they say. Well, it turns out the distribution of matter sort of affects the angle measurements and the length measurements at every point. And you can ask if you have a vector in your space-time, that's some real space that has some gravitation on it because you've got some suns here, some stars there, some really fat guy there, whatever, the things that are distorting your gravitational field. And if you move something around, you have some path. You go from here to Penang and back, but maybe not the same way. You go from here to Penang, take a boat to Borneo, and then come back here. And the whole time, you're being very careful to keep your hand like in a very rigid position, so that your arm, you're being careful that along your entire path, your arm is always pointing in the same direction relative to the direction of your travel. Okay. So you can do this. That would be a very silly thing to do, but you can do it. And so you do that. So you do this kind of thing in such a precise way that you can measure infinitesimal differences that are due to general relativity. And in fact, your position of your arm will have changed slightly during this path, and that's the holonomy of the path. And so the curvature you can measure. So the curvature just needs to know how much when you move around the path your vectors change. And the curvature and the curvature in general relativity is exactly gravity. That when you write down the field equations for how particles move in space, the Einstein field equations, this gives you some way to move vectors around. And when you have a way to move vectors around, you have curvature via exactly the same apparatus I sort of sketched before. And in that case, it's exactly what gravity is. And the other example that's very important in physics is in electromagnetism, where so recall that you have Maxwell's equations. If you haven't seen them, well, you can treat it. Whether or not you've seen them, they are Maxwell's equations. And recall that a vector potential. So this is the electrical field, and this is the magnetic field. These are some differential equations that the motion of particles and about how a charged particle moves in a vector in the presence of an electromagnetic field. And there's something called a vector potential, which is some vector such that the del cross it is equal to b. Okay. This thing turns out to have the exact identical mathematics as the things I was describing. Vector potential tells you how if you move some particle around in a vector field, then you have some vector sticking out of it. How these change. Okay. What are you actually moving around? So it actually tells you about if you have some. So for this point of view, we don't view matter as being sort of individual point things, but so here I'm actually really talking about relativistic quantum mechanics. But you view matter as a probability distribution, like you do in quantum mechanics. The particle isn't here. Okay, I'll finish one second. The particle isn't here, but it's here with some certain probability. And the probability is a complex number in quantum mechanics for reasons that are very deep and mysterious. And so what you have is for every point in space, you have a copy of the complex numbers. But the thing is, it's not really a copy of the complex numbers. It's an abstract two-dimensional vector space. You don't know which one is 1 and which one is I. But you can still add things and you can multiply them. So they're vector spaces, and you don't know which one is which. And in fact, you can't even measure which one is which, because the thing is, so when you are taking to see what the property is of a particle is where you're taking the length of the complex number. So you can measure the length of a complex number and that's physically meaningful, but the angle it's at is not meaningful. However, the amazing thing is that if you now take your particles or your mass distribution satisfying the Schrodinger equation or whatever, you act on it, moving it around using the vector potential, it will move around. Like, it's just like the vectors that I talked about before. You've got some, it's this probability vector in complex space will move around. The length is physical, but the angle isn't. The thing is, the amount you move by is physical. So that is, even though you can't actually identify, to identify a single one of these complex two-dimensional vector spaces with R2 would be saying that the angle is a physically meaningful thing. Because if you could do that, if it were sort of a coordinate invariant thing, that you could if you could actually find an experiment that told you what the angle was, then you could identify what any vector in the plane was. Because the length you know, and if you could identify the angle with some experiment, then you would have identified every vector in the plane with a point in R2, because you know its length and you know its angle. It turns out there's no experiment that will measure the angle. However, if you move around so that you can measure the difference between two vectors, how much this vector changes when you move around, the difference between the two angles is meaningful physically. There's something called the Bohm-Aharonov, how do you say the guy's name? Aharonov-Bohm effect, where you can essentially measure the holonomy physically. You have electrical particles, you move them around, you can measure how much the angle changes. So you never know if this angle is 0 or pi over 2. It's not physically meaningful, but you can measure the difference. So I'm being pulled off the stage, but that was about where I wanted to end anyhow. Thank you for your attention.